Welcome to my technical channel. My name is Sasha, and in this video we will discuss the design for manufacturing and the reverse engineering, and also design for manufacturing for the 3D printing. And at the moment you know that the 3D printing is really hot topic, and I want to discuss with you how you make the decisions with the design and what the thoughts I have when they design the new product based on the technology FDM 3D printing and the printer which I have at home. I will show you how to make decisions in a design, and also I will show you how make a slicing and also optimize the quality of prints for this particular product. And this whole combination of the decisions is also called design for manufacturing. It means from the beginning I already know which technology of production I will use, and I design and adopt designs accordingly. And it saves a lot of time and also saves a lot of effort, and additionally it saves cost of production and also make the production more reliable, and you spend less time in troubleshooting later. Today we will discuss how I designed and produced these two plastic parts, which goes on already existing plastic black stem, and these two parts should be reliable and compliant with the already existing design mass produced in the industry, and this is one of the additional complications for the design. From the initial thought, I actually take the competitor, and my competitor took this kind of a drum for the paper. So you insert the paper inside and you rotate it inside the chemistry. And the two things what I want to mention about this initial drum, it's quite huge, it's quite heavy, and it's overcomplicated, and also have a lot of decisions on a design which doesn't really work well with the mass production and 3D printing. What I want to mention here also, it consists from the two different parts, and so it's quite hard also put them together because they break some rules with the compliance of the materials, and also doesn't really design it well to have the proper fit. And as a good engineer, I took inspiration from these reels. This reels is for Patterson tank for film development, and they goes on exactly the same stem. So let's start with looking on the parts and discussing the design ideas and my steps forward, and I will also show you intermediate results of my experiments and how I print them and what the logic behind it. I want to start discussion with the constraints. So as you can see, I have an outer diameter of the drum and I cannot void this diameter. So it means I always will be stuck with this diameter because the drums itself can be a little bit different. So this is my limiting factor for the outer size. So the competitor design is also mostly stick with this outer size. And what I want to see here, because it's exactly the same stem. So as you can see, this reel goes in several parts. So you have a part which is rotating in the middle, but what we're curious about is this middle part. So basically it goes on top of the stem and it have a quite nice snug fit. What we want to see here, it's important part, drum, it's a pin. And you can clearly see it here from that side. So, and basically this pin is protrude inside and have a special design, so it's going out. If you can see it here like this, you have a pin which is pushing on top of the stem. But in general, you have a tolerance gap. So you have a gap and your stem goes freely inside this diameter. But at some point, you can see here that the pin is actually have a tension and pushing the rod against the wall. And this is kind of a spring action provided with this part, gives you reliable and good rotation of the part, so it doesn't really go anywhere. As you can see, it's quite snug and really good fit. And idea of the design here, as you can see, it's more or less the same type of the pins. It's really hard to show them there, but you can see here that they exist and should provide more or less the same action. So it's quite snug, but the downside is not enough length. And as you can see, I can pivot this portion of the stem. And if we look here, the distance where the stem can be pivoted is completely different. So here it's more snug just because the length is higher. So this is the first decision what I want to copy. And the second one, as usual, you have the facet here, which allows you to insert the stem much easier. So these two decisions I want to take and also make it in my design. Downside of this design is the thickness. So it's too thick and too heavy. And additionally, I don't really like this idea of the top part, which helps to support middle stem up to the end. As you can see, it doesn't really have orientation. It wobbles there. And the idea how it should work, for me, not really clear. But you can see here that it's the same kind of a problem. It wobbles a little bit, but here it works a little bit better. So the idea of this part is clearly seen, and you can understand how it works. So you have a pin which is printed inside and create the snug fit. So I started with the bottom part. And as you can see, I more or less take a inspiration from the combination of this cup and from the reel for the film. So it's same size from outside, and it's the same size on the inner core. But as you can see, I make a much bigger entrance bevel. That it means that I can put the stem how I want, because it will be operated in dark, and it's much easier to shovel it there. So it's no problems whatsoever. But because we're using 3D printer, I know the tolerances, and I also know what is possible to print, because orientation of the print on this part will be bottom up. And as you can see here, you see the pattern from the table. So it means the angle of this bevel here should be not more than the 60 degrees. So if I make the 45, it can be a defect here on some kind of a printers, on not modern ones, or if you print too fast, or you have problems with the material. So think about that. And if you make the longer path here, and also it works exactly the same, but you remove the problems with the printing. And as you can see it here is definitely 45 degrees, which is a downside of the printing, and it creates less support to put the stem inside. And I want the design to be simplistic, so it means that the chemistry should go in this direction without any problems, and it should rotate inside the drum. So if the chemistry goes inside, I have no problems whatsoever. So, but you can see that I try to do exactly the same as I have here on the reel, so to be more or less transparent, but also have a support for the middle stem. So what I did, I add additional bevels, because I don't want to be printed with several layers here and have a 90 degree to the walls. So as you can see here inside, I have additional bevels. I will show you how the design looks like on a computer, and you will understand my additional thoughts here. I just want to start with a physical example. And also here I have a compliance pin, which works exactly the same. And I have the same bevels from the top and from the bottom. And as you can see, it perfectly works without any problems and have snug fit. It's even squiggle there. And because it's made from the plastic and PLA, if this fit doesn't really work and or create some problems over time, you can use the heat gun and bend it a little bit inwards. So as I said, this tool used for developing of the paper. And the main thing here, I want to have this bottom cup always on a stem in the dark, so I can pull it and push it with the one hand. And additionally, I want something to support paper on top. And my initial idea was to have something like this, so have a ring and to push the paper inside with a ring and have a support on the paper. So this is my initial design thoughts. And as you can see here, I have several problems. This thing is a little bit too flimsy, so it doesn't really support well its print itself. But also in the same time, I just copied the same stem with the bevels from the both sides. And I just need to modify this portion to be more sturdier and more just rigid. But also here have additional points of the connection, so I make it more round from these two sides. And also I make additional support here for the connection, because otherwise it will be 90 degrees and this stem will be too flimsy to hold anything. So here, this is the first iteration. And on the next iteration, I thought like, yeah, okay, but what is the paper if it's paper a little bit bigger? So this is why I make this additional loop here. First of all, it creates more rigidity and springiness, but as you can see, it doesn't solve this spring action, but it solves more or less this spring action. My initial thought was, okay, I want to do it with the one hand, or at least with a one hand and a finger like this. So if I wrap it around and paper is too big, as you can see, I can get stuck on this edge. So I cannot push it here if it's 90 degrees. But what I always can do, I can bend it more and push it inside this hook action. I hope you can see it better here. You can see that I have space to put the paper first and not get stuck with the corner if I have a paper in this kind of a direction, especially in the dark. So I can bend the paper to this notch and push it down. So the last thing what I want to solve, as I said, is the flimsiness, because I cannot normally remove this. So it bends, so I need a reach inside, and I don't really like this action. So I make everything a little bit more sturdy and a little bit more rigid. So I added layers and the thickness. And this is a final version of this adapter. And as you can see here, the final version of the adapter works perfectly fine. And you can push the paper and it works. And it works for any type of size of the paper, and the paper can rotate. So that's it for the physical review of the thing. So let's go and see the design and design decisions in the CAD, and also how I sliced the whole thing and how I printed. I have several options how I can design this piece, but I started with what I can measure, because this is a little bit of the constraints what I have, and I call them outer wall, and I also have the wall thickness, I have a rod diameter, and I also have the internal wall thickness, which is exactly the same thickness. The logic behind that, I have the parameters here, so I have a rod and I have a rod thickness, and also I have the thicknesses of the bottom plate and all the parameters which I can deal and change later. So what is important, I have the wall thickness. As you can see here, it's a calculation. So I have 0.6 millimeters multiplied by 3. So it means I want to print with a 0.4 millimeter nozzle, and I want to set up the line with a 0.6 and have the 3 lines. So outer wall will be 3D printed with the 3 solid lines with exactly the same size. And this is the idea, and this is how I want to see this kind of a print happens. So if we close this one and we go here, and as you can see here, the first step what I do is extrusion, and extrusion is 1.8 millimeters. So it's exactly the same as a wall thickness, and I just like it and use less amount of the variables because it saves a lot of time and your design will be more or less proportional. So here I have additional extrusion, and as you can see, this extrusion is going up as a cup, and this is a depth what I measured from the outer wall of the development cup. So this design looks more or less like we discussed, but as you see here, I don't have any support for the 3D print here. If I turn off the sketch, you can see here is a 90 degrees, here is a 90 degrees, here is basically straight. So it's a rough estimation of what we need. So from here, I need to make it more functional. So to make it more functional, I start to drawing the plane. And to draw the plane, I used the tangent to the inner cylinder. And from here, I draw on this plane the hole cut out and basically created the pin. And I will just skip to the end of that. So how it works, I have the pin, which I started from the hole. I made a middle plane 90 degrees to this hole. And from here, I make a sketch of the shape of the pin which I want to see, and I make a revolve of this pin to basically accommodate the shape inside. So the next step, I made the sketch. So the sketch for the holes inside the base. And I make the sketch, and from here I use the plugin which called Lighten, and just made the circular pattern to have exactly the same. You can experiment with that, but I just end up here, and I really like how it works and looks, and it's more or less functional. So next step, I apply chamfers, and the chamfers quite simple because it's printed up. It's 45 degrees, and also I make the wall thickness parameter here, and it's exactly the same here for the bottom part, but for the bottom, as we discussed on the physical product, I have a 70 degrees, so it's an inclination of the 30 degrees. And if we go in here with the top one, so it's more or less the same copy of the bottom one, but just in a different direction. So here I also have a chamfer for the paper to go easily inside. And basically that's it. This is our bottom cup. And if we go for the top part, but if you can see here, it's exactly the same part. So I just copy design and doesn't really make the bottom. I make only inner cell, and here it's exactly the same pin. So as you can see here, I made the chamfer, and this chamfer will help me to put the paper inside. And I just made them symmetrical. And as you can see here, this chamfer is also 70 degrees and with a distance 1.2 millimeters. So I just make it, eyeball it, and make it reasonable for 3D printing. So here on the outer side of the wall, inner side of the wall, I have exactly the same chamfers. This part is much easier and in the same time have exactly the same design logic and prints really well and really fast. So from here, let's go for the slicing, and I will show you how to slice these two models. So here, as you can see, I have the Bambu A1 table. This is a printer what I have at home, and I have the settings and I want to print them, for example, from the PLA, and this is my two parts. So to slice them, I will use a layer height of 0.2 as kind of a strongest setting for the 0.4 nozzle. So I will set up everywhere 0.6 millimeter for the line. It's a little bit rough for the detail work, but in our case, as you remember, we designed everything for 0.6 millimeters. I also introduced the strength here, and I just will use the rectilinear base, and also I will put the 100% in fill, but it's not really necessary for this model if I have the bottom shells and top shells to the 5. So basically everything is a shell. So if I go to the speed, this printer can print crazy fast, but I want the print will be reliable. So I limit it to 100 millimeters per second. And also I have the normal speed printing up to 2000 millimeters per second. And this 2000, it's more or less tested acceleration, which this printer will produce excellently fine and doesn't really create the defects with the input shaping on the printer. So I press slice, and as you can see, it's working here quite well, and after the slicing, I will get the time estimation for both of the parts. So as you can see here, I have filament, and if I go to the summary, I will print these parts with a 1 hour 38 minutes and spend mostly around 50 grams of the filament, which is quite nice. And if we inspect the whole thing, how it's sliced, I honestly prefer to set up the seams myself, but in this case, as you can see, it's quite nice. So the seams is on the edge, and the outer seam will be a little bit ugly because I have 0.6 millimeter layers here, outer wall. If you want a little bit better look, you can put it with a 0.42, but for a functional part, it's quite nice. And as you can see here, if I roll it down for both of the parts, I don't really have the infill. So I have only walls, and the walls will go from the bottom to the up, and this portions of the print will support the strength. You can also add the ribbon here, but it's really not necessary. So if it's not necessary, it will save time with the printing if you not have it, and also save the filament. So if you go up, you have the exact 3 walls, and on top, these 3 walls goes to the two walls and thin down because I have Arachne turned on. So this algorithm actually change the size of the lines, depends on the thickness of the design. Basically that's it. You can make the design print faster, but I think 1 hour 30 minutes it's quite nice for this design and reproducible. And also you can clone them around the table and produce at least 2 pieces per one set. So 2 sets per one print. Thank you for watching, and I hope my design for manufacturing will help you design your parts for the 3D printing. So in this channel there will be a lot of new things about the microelectronics, about assembly, about the 3D printing, about the migration, work migration, and any type of motivation around the work and the profession as engineer. So stay tuned, subscribe to my Telegram and the Instagram. You can find them under the description under this video. Thank you for watching and see you next time.